Illustrative Math, Algebra 2, Unit 4, Lesson 15 is called Using Graphs and Logarithms to Solve Problems, Part 1. Goal today is I can solve exponential equations using logarithms or by graphing. All right, warm up. Here's a graph that represents an exponential function with base e, defined by f of x equals e to the x. So think of it as y equals e to the x. Explain how to use the graph to estimate logarithms such as ln of 100. So ln of 100, if I set it equal to y, ln of 100, let's make it equal y. So that means e to the y equals 100, or maybe set it equal to x. Let's do that. Set it equal to x. Well, now here's e to the x, and e to the x is equal to y. So if I wanted to estimate 100, I would graph y equals 100. And this is y equals e to the x. Whoops. And I'm going to see where they intersect, which looks like right there, which is about 4.6. Okay. So what I would do is here to explain it, I would say I'm going to graph e to the x. Oops, what did I do? Here, I'll just write it. So I'm going to graph y equals e to the x and y equals 100 and see where they cross. So my estimate was approximately 4.6. How can you use your calculator to check your estimate? Well, we could type in e to the 4.6, and then we can type in ln of 100, because this will give me a closer answer than this, and I'm going to see if they're close. So type it into my calculator. E to the 4.6 gave me 99.48. ln of 100. ln of 100 gives me 4.605. So this is a little bit closer than 4.6. My graph was, I did pretty well on that. When I checked it, I see that it's still not quite right. So if I were to do it with this, or to say e to the 4.605, is probably going to be a little bit closer to 100. So I do e to the 4.605, and I got 99.98. So a lot closer. So that's good. All right, so here's an expression. 1 times e to the 0.6t models the balance in thousands of dollars of an account t years after the account was open. What is the balance when the account is open? So that means we're going to let t equal 0. So, or you could think of it here as this is the initial value, and this is your growth rate. So you're growing by 6% each year. So 1,000 is the initial, because it says 1, but it's in thousands. Okay, so that's how I get that. And then grows 6% each year. So that's our growth rate up there for continuous growth. Okay. So after 1 year, we're going to plug in 1 for t. So 1 times e to the 0.06 times 1. So I'm going to get 1.06 1.62, which is in thousands, so it's $1,062. After 2 years, it's 1 times e to the 0.06 times 2. So it's going to be e to the 0.12. So I get 1.127, which is $1,127 because it's in thousands. Diego says that the expression ln of 5 represents the time in years when the account will have $5,000. Do you agree? Explain your reasoning. So, well, let's take the equation and set it equal to 5. 5 equals 1 times e to the 0.06 t. So get rid of the 1 because I could divide each side by 1. 5 equals e to the 0.06 t. Let's solve for t. So I'm going to write it in log form. So it's going to be log base e is ln of 5 is 0.06 t. So he's close, but to get t by itself, I'd have to divide by 0.06. So this would actually give you the time that it would take. So if I type that in, ln of 5 divided by 0.06, I get 26.8. Okay. Suppose you open this account at the beginning of this year. Assume that you deposit no additional money and withdraw nothing from your account. Will the account balance reach $1 million and make you a millionaire by the time you reach retirement? Show your reasoning. So I guess this question is kind of interesting because you know everybody's gonna have different numbers. So I guess when do you retire? Let's say you retire at 65. I don't know. And let's say you're in Algebra 2, 15 years now. 15 years old now. Sorry, that was sloppy. 15 years old now. So your timeline is going to be 50. So we're going to have to take that number 1 times e to the 0.06 times 50 and see if it gives me, it would need to give us 1,000 because it's in thousands. So take your calculator. I don't really need to do 1 times. I'm just going to do e to the 0.06 times 50. And I got 20. So 20.086. Okay, so if it's in thousands, it's going to be way off. It's going to be 20,000 approximately, or 20,086. So I would say no, not even close to $1 million. Okay. Let me double check this here. Yeah, you start out with 1,000. So you'd have to play around with this number here to see when it would equal 1,000, but because that would give you $1 million if it equals 1,000. So you could plug in different numbers and see what it is to kind of see how long it would take you. You're gonna have to put in more than 1,000 to start. All right. A population of cicadas is modeled by a function defined as f of w equals 250 times e to the 0.5 w, where I guess that should say w is the number of weeks since the population was first measured. Explain why solving the equation 500 equals 250 times e to the 0.5 w gives the number of weeks it takes for the cicada population to double. Well, I would say this is my initial value, 250 initial value, and then it equals 500, which is double 250. It's 250 times 2. All right, how many weeks does it take to double? Show your reasoning. So I'm going to use some algebra here in logarithms. So 500 equals 250 times e to the 0.5 w. So I'm going to divide by the 250, get rid of that multiplication. So I get 2 equals e to the 0.5 w. Now I'm going to write in log form. So log base e is ln of 2 equals 0.5 w. Divide by 0.5, and there's your exact answer. That's how many weeks. Now you might say, well, that doesn't really mean much to me. So you could use your calculator. Ln of 2 divided by 0.5, and I get 1.386 weeks. Okay, so take your function, double check it. Let's find f of 1.386. Let's see what I get. 250 times e to the 0.5 times 1.386. And sure enough, it gave me 499.93. Okay, so it looks like it worked. Okay. Use graphing technology to graph y equals f of w and y equals 100,000 on the same axes. Explain why we can use the intersection of the two graphs to estimate the cicated population will reach 100,000. So we start with 250 initial. Remember, f of w is 250 times e to the 0.5 w. Now I'm going to use x and y just to show you your graphs. So this is going to be weeks, x is weeks, and this is your population. So you start down here at 250, almost looks like 0, it's so spread out. Here's y equals 100,000. Here's my graph. This was the y equals 250. Here, let me move that graph over here. That's the red. And this is y equals 100,000. Now, obviously, I changed my axes. So, and when you go to make your x, I would make my x minimum, a little bit less than 0, and make your max for x. Looks like I got it at 17. I made my y's go from a little bit less than 0, like up to 100, a little bit more than 100,000, probably like 110,000 in all honesty. Okay, so make sure you get your window set. Clearly, we can see here from that intersection point, it's 11.983 weeks. We want to know when they're equal. All right. So I added a few problems. These aren't in your book, but they're very similar to what we're doing. So we're going to jump in here. Element X decays radioactively with a half-life of 15 minutes. If there are 770 grams of element X, how long to the nearest tenth of a minute would it take the element to decay to 32 grams? So 770 is your initial. 1/2, you're multiplying by 1/2, and then it's going your time every 15 minutes, it decays by 1/2. So we want to know when that equals 32. So I'm going to graph this. I'm going to use x instead of t, and then I'm going to graph this, and I'm going to set it equal to y. I just want to use the graph to solve, okay? So if I look here, y equals 32 is down here. And then this here is y equals 770 times 0.5 to the x over 15. And you can see where they intersect, and it's 68.831. And what is it? That's minutes, right? So minutes. Okay. Here's another one. Person invests $4,500 in a bank. The bank pays 5.25% interest compounded monthly to the nearest tenth of a year. How long must the person leave the money in the bank until it reaches 6,400? So 6,400 is what it equals. We start out with 4,500, 1 plus my rate. So my rate is 0.0525 divided by n. N is how many times it's compounded, so I put that over 12. And that's times the 12t. So I'm going to kind of simplify this here. It's 4,500 times 1 plus 0.0528 divided by 12. So I get 4,500 times 1.0044 to the 12t power. So I'm going to graph y equals 6,400, and then y equals 4,500 times 1.0044 to the 12t, or probably use x on Desmos. So here's my two functions. Okay, I must have rounded that to the 0.44. Let me double check that. 0.0528. I don't know why I put the 28 there. That's silly. Actually, I don't know, where did I get the 28? All right, so anyways, 2.5, I'm sorry. It's 2.5. Let me try that again. 0.0525 divided by 12 plus 1. There we go. It's more like 0.44. But I rounded this, so actually it's going to be 0.4375. That'll make it a little bit more accurate. So then the intersection point is where they are. So it's 6.724. And what was it? Years? To the nearest tenth of a year. So to the nearest tenth, I would say 6.7 years. Okay. All right. How are the functions and problems in this lesson like those we've seen in the past? I would say they're exponential functions. So exponential equations are functions where the variable is in the exponent. How are they different? I would say we use graphs to solve them. We graph the left side of the equation and the right side and see where the two graphs intersect. Actually, I'm going to say we graph the left side and the right side by setting each side equal to y. And then we see where they intersect. All right, what are some benefits to finding unknown exponents by solving equations? What are some benefits finding unknown inputs by finding the intersection? So I would say that using algebra to solve them allows us to get an exact answer with a logarithm. Using a graph allows us to get a decimal answer very quickly. All right, I can solve exponential equations using logs or by graphing. I guess I really only graphed on these, so maybe I should go back to one of these and maybe use logs here. Maybe this one here. So let's go back here to this one. So I guess I did use logs. I used logs here on this one, so I guess we're okay. All right, on to the last one. Cool down. The equation A equals 4 times e to the 0.45 m represents the area of a wall A in square feet covered by mold m months since the mold was first spotted. The area of the wall is 80 square feet. Use the graph representing F to estimate when the entire wall will be covered in mold, if not cleared. So we needed to graph y equals 80. So that'd be like setting this whole thing equal 80 equals 4 times e to 0.45 m. So this is my m axis. This is my a axis for area. So if I graph y equals 80, or I guess technically I always do that. It's a equals 80. There's that line. It looks like they intersect at 6.6 weeks. Write and solve an equation to find the approximate number of months it would take the mold to cover the entire wall. So I'm going to go back to this equation that I had here, and I'm going to use some algebra to solve. So divide each side by 4. That'll give me 20 equals e to the 0.45 m. Now I'm going to write it in log form. So log base e is ln of 20 equals 0.45 m. Now I need to divide by 0.45. So I get m equals ln of 20 divided by 0.45. That's my exact answer. Let's check and see how close I was on my graph. So I type ln of 20, natural log of 20, divided by 0.45, and I got 6.66 weeks. So we were close. Obviously, this is much more accurate, but obviously the graphing method is much faster. All right. Well, thank you for watching, and hope you enjoyed this video. We'll see you next time.